Here's a question that sounds morbid, but stay with me. When you die, where do you go? I am not talking about heaven or hell. I am a physicist, and I am asking something far more interesting. Where does the stuff that is you actually go? Because here is what is strange. You have about 7 billion atoms in your body right now. That is a 7 followed by 27 zeros. 7 octillion atoms. And when you die, not one of those atoms disappears. Not a single one. They are all still here. So if nothing is lost, in what sense are you gone? That is what we are going to figure out today. By the end of this, you will understand something profound about what you are made of, where it came from, where it is going, and why the very idea of you is stranger than you ever imagined. I think you will never look at yourself, or a blade of grass, or a distant star, or even a breath of air quite the same way again. Let us start with something simple. A candle. You light it, and it burns. The wax melts, the wick glows, and after a while, the candle is gone. You might say it has been destroyed, but that is not quite right, is it? Where did the candle go? Some of it turned into light, photons that bounced around the room and got absorbed by the walls, warming them slightly. Some turned into heat, which spread through the air, and the carbon in the wax combined with oxygen to make carbon dioxide, now floating around, maybe drifting out the window, maybe being breathed in by someone walking by outside. The candle did not vanish, it transformed. Every atom that made it up is still somewhere, just rearranged into different configurations, different molecules, different forms. This is one of the most fundamental laws in all of physics. Energy cannot be created or destroyed. It can only change from one form to another, the first law of thermodynamics. And I want you to understand, this is not just a good approximation. In every experiment ever conducted, in every observation ever made, this law has held. It is as close to an absolute truth as physics has ever found. Now here is where it gets interesting. You sitting there listening to me, you are not so different from that candle. You are, in the most literal sense, burning right now. Your body is taking in oxygen, combining it with food, and releasing energy. But let me tell you exactly how much, because the numbers are extraordinary. At any given moment, your body contains about 250 grams of a molecule called ATP, adenosine triphosphate, the energy currency of life. Every cell uses ATP to do work, to move, to build proteins, to think. That 250 grams represents only about 4 watts of power, the equivalent of a small LED bulb. That is all the ATP you have at any moment. But your body uses far more than 4 watts. At rest, you are burning about 80 to 100 watts. Exercising, maybe 500 or more. So how does that work? Your cells recycle ATP at a furious rate. Each ATP molecule gets used and regenerated about 1,000 times per day. Your body produces, uses, and regenerates roughly your entire body weight in ATP every single day. 40 to 70 kilograms of ATP made fresh every 24 hours. Over the course of a day, a healthy person produces about 1/200 watts of total energy, enough to power 1/200 light bulbs simultaneously. And where does this happen? In tiny structures inside your cells called mitochondria. You have about 10 million billion of them, 10 quadrillion microscopic power plants, each one burning fuel and churning out ATP. Here's something remarkable about mitochondria. They have their own DNA, separate from the DNA in your cell's nucleus. This is because they used to be free-living bacteria. About 2 billion years ago, one of our single-celled ancestors engulfed a bacterium but did not digest it. Instead, they formed a partnership. The bacterium provided energy, the host provided protection and nutrients. Over billions of years, that bacterium became your mitochondria. You are, in a very real sense, a colony of organisms. Now consider your brain. It is only about 2% of your body weight, yet it uses about 20% of your energy. A single thought, a single memory being formed, requires billions of ATP molecules. Each neuron firing requires about 1 billion sodium ions to be pumped back across cell membranes, which means about 1 billion ATP molecules just to reset that one neuron for its next signal. When that symphony stops, that is death. Not because the atoms go away, but because the process stops. the pattern stops being maintained. And just like the candle, you are constantly releasing atoms into the world. Every breath you exhale carries away carbon dioxide, carbon that was part of your body a moment ago, now floating free. Every drop of sweat releases water and salts. Every shed skin cell is atoms leaving your body. You lose about 30,000 to 40,000 dead skin cells every single minute. You are not a static thing. You are a process, a river of atoms flowing through a particular pattern we call you. Now suppose you wanted a physicist to speak at your funeral. Here is what I would want that physicist to say. No energy gets created in the universe and none is destroyed. All your energy, every vibration, every bit of heat, every wave of every particle that was your beloved, it all remains in this world. The photons that bounced off your face, the particles whose paths were interrupted by your smile, by the touch of your hair, hundreds of trillions of them. They have scattered into the world like children running in all directions. They are still out there. They will always be out there. According to the law of conservation of energy, not a bit of you is gone. You are just less orderly, that is all. But let us go deeper, much deeper. Let us ask where those atoms came from in the first place. Pick up your hand and look at it. By mass, you are about 65% oxygen. Surprised? Most people are, but remember, you are mostly water, and water is H2O, and oxygen is the heavy part. One oxygen atom weighs 16 times as much as one hydrogen atom. After oxygen comes carbon at about 18%, then hydrogen at about 10%, then nitrogen at about 3%. Together, these four elements make up about 96% of your body mass. Just 4 elements out of the 92 naturally occurring ones. The remaining 4% includes calcium in your bones and teeth, phosphorus critical for your DNA and ATP, and trace elements, iron, zinc, copper, iodine. The iron in your body, if you extracted it all, would make a nail about 3 inches long. That is it. But without that tiny bit of iron, you could not carry oxygen in your blood and you would die in minutes. By number of atoms rather than weight, you are about 63% hydrogen, 24% oxygen, and 12% carbon. The vast majority of atoms in your body are hydrogen. The simplest atom, just 1 proton and 1 electron. And here is a striking way to think about it. There are more atoms in your body than there are stars in the observable universe. The observable universe contains roughly 200 billion galaxies, each with roughly 200 billion stars, about 4 times 10 to the 22nd power stars. But you have 7 times 10 to the 27th atoms. You contain about 100,000 times more atoms than the universe has stars. Now consider the carbon atoms in your skin. Where did they come from? You ate them. They were in your food, maybe in bread, or a carrot, or a steak. And where did the bread get its carbon? From the wheat plant, which pulled carbon dioxide out of the air during photosynthesis. And where did that carbon dioxide come from? Other plants and animals that breathed it out, decomposed or burned. But trace it back far enough, and you reach a remarkable place. The carbon in your hand was not always on Earth. It was not even made on Earth. It was forged in the heart of a dying star. Let me explain this carefully, because it is one of the most beautiful things we have ever discovered about the universe. Just after the Big Bang, about 14 billion years ago, the universe had only the simplest atoms. At the very beginning, in the first fraction of a second, there were not even atoms, just a soup of quarks and gluons, so hot and dense that nothing we would recognize as matter could exist. The temperature was over 1 trillion degrees. As the universe expanded and cooled, quarks combined into protons and neutrons. This happened when the universe was about 1 microsecond old. Think about that. 1/1,000,000th of a second after the Big Bang, the building blocks of all matter came into existence. In the first 3 minutes after the Big Bang, the universe was a roiling soup of particles at unimaginable temperatures. At 1 second old, it was still too hot for simple atomic nuclei to survive. Protons and neutrons were forming and breaking apart constantly. At that moment, there were about 7 protons for every neutron. Why? Because neutrons are slightly heavier than protons, and in the hot conditions of the early universe, the reactions that converted neutrons to protons happened slightly faster than the reverse. This ratio would turn out to be crucial for the chemistry of the entire universe. As the universe expanded and cooled, something remarkable happened about 3 minutes after the Big Bang. Protons and neutrons began sticking together. First, they made deuterium, heavy hydrogen, 1 proton and 1 neutron. Then helium-3, then helium-4, and a tiny amount of lithium-7. The timing was everything. By about 3 minutes, the temperature had dropped to about 1 billion degrees, cool enough for nuclei to form, but still hot enough for fusion to happen. This window lasted only about 17 minutes. By 20 minutes after the Big Bang, the universe had cooled too much, the density had dropped, the particles were too far apart, and the cosmic nuclear reactor shut down. The result was a universe that was about 75% hydrogen by mass, about 25% helium, a trace of deuterium, and a tiny bit of lithium, and nothing else. No carbon, no oxygen, no nitrogen, no iron, no calcium, none of the heavy stuff that makes up rocks and trees and people. There was a bottleneck. There is no stable nucleus with 5 nucleons or 8 nucleons. 2 helium-4 nuclei combined would make beryllium-8, which falls apart in about 10 to the negative 16 seconds. There was simply no way in those first 20 minutes to build anything heavier than lithium. So where did all the heavy elements come from? They had to wait for stars. The first stars formed about 200 million years after the Big Bang, when gravity pulled together primordial hydrogen and helium into dense clouds that collapsed and ignited. These first stars were monsters, 30 to 300 times the mass of our sun, burning hot and bright and fast. A star is a giant nuclear reactor. In its core, under tremendous pressure and temperature, hydrogen atoms fuse together to form helium. 4 hydrogen nuclei smash together and become 1 helium nucleus, releasing energy. That is what makes the sun shine. That is the power source that has kept our star burning for 5 billion years. But in more massive stars, the story goes further. When the hydrogen in the core runs out, the core contracts and heats up. If it gets hot enough, about 100 million degrees, something remarkable happens. Helium atoms start fusing into carbon. This is called the triple alpha process, and it is a delicate thing. 2 helium nuclei fuse to form beryllium-8, which is wildly unstable, falling apart in about 10 to the negative 16th seconds. But if in that tiny window a 3rd helium nucleus comes along and collides with the beryllium-8, you get carbon-12, stable carbon, the backbone of every organic molecule in your body. Here is something remarkable about this process. The reaction rate depends on temperature to the 40th power, the 40th power. If you double the temperature, the reaction rate increases by about 1 trillion times. The physicist Fred Hoyle actually predicted that this reaction must exist, based purely on the observation that carbon exists in the universe. He said, in effect, if carbon exists, there must be some way to make it. There must be a resonance, an energy level in the carbon nucleus at exactly the right energy to make this reaction possible. When experimenters looked, they found exactly the resonance he predicted, at 7.65 million electron volts above the ground state. This is sometimes cited as evidence for the anthropic principle, the idea that the universe must have the properties that allow for the existence of observers like us. If this resonance did not exist, if the energy levels were even slightly different, carbon would not form efficiently in stars, and we would not be here to wonder about it. Nature had to be precisely tuned for carbon to exist, and here we are, made of it. The story does not stop at carbon. In massive stars, the fusion continues. Carbon fuses with helium to form oxygen. Oxygen fuses to form neon. Neon to magnesium. Magnesium to silicon. Silicon to iron. But iron is the end of the line. When you fuse lighter elements together, you release energy. The products weigh slightly less than the ingredients, and that missing mass becomes energy according to Einstein's famous equation. But iron is at the bottom of the binding energy curve. Fusing iron does not release energy. It absorbs it. It is like trying to roll a ball up a hill instead of down. So when a massive star builds up an iron core, the core can no longer generate energy to hold itself up against gravity. In less than a second, an iron core the size of the Earth and with the mass of the Sun collapses into a ball of neutrons just a few kilometers across. This gravitational collapse releases more energy than our Sun will radiate over its entire 10 billion year lifetime. The outer layers of the star are blown off in a catastrophic explosion, a supernova. For a few weeks, a single exploding star can outshine an entire galaxy of 100 billion stars. And in that explosion, in those brief catastrophic seconds, something magical happens. The conditions become so extreme, so hot, so dense with neutrons that elements heavier than iron can form. This is called the R process, R for rapid. Neutron capture happens so fast, millions of captures per second, that nuclei build up faster than radioactive decay can tear them down. An iron nucleus absorbs a neutron, then another, then another. In seconds, it has captured dozens of neutrons and become wildly unstable. But before it can decay, it captures more. The nuclei race up the periodic table, becoming gold, platinum, uranium. In 2017, astronomers detected gravitational waves from two neutron stars colliding and pointed their telescopes at the source. They saw the glow of newly formed heavy elements, including gold, being forged in real time. We watched the universe make gold. That kilonova produced about 10 Earth masses of gold in seconds. That is where much of the gold in your wedding ring came from, neutron star collisions. All of this material, everything the star spent millions of years building in its core, everything the supernova or neutron star collision created in seconds, gets flung into space at 10,000 kilometers per second. It mixes with interstellar gas clouds. Those clouds eventually collapse under their own gravity to form new stars, new planets, new everything. Our sun is a third-generation star. The dust cloud that formed the solar system was already enriched with heavy elements from earlier supernovas. The Earth condensed from that dust about 4.5 billion years ago, and you, every atom of carbon and oxygen and nitrogen and calcium and iron in your body, you are made of star stuff. This is not poetry. It is fact. The iron in your blood, the same iron that carries oxygen from your lungs to your tissues, was forged in a star that exploded before the sun was born. The calcium in your bones came from the dying breath of a red giant. The phosphorus in your DNA was created in a supernova. Speaking of DNA, a single human cell contains about 3 billion base pairs. If you stretched out all the DNA in one cell, it would be about 2 meters long. You have roughly 37 trillion cells, most with a complete copy of your genome. If you stretched out all the DNA in your body end to end, it would reach from Earth to the Sun and back about 600 times, over 100 billion kilometers of DNA. And that DNA is constantly being copied, checked, repaired, and read. Every second, your cells are reading millions of genetic instructions, building proteins, maintaining the patterns that make you you. Now let me tell you something that might surprise you. Those atoms in your body, most of them were not there a year ago. Studies using radioactive tracers have shown that about 98% of the atoms in your body are replaced every year. This was first discovered in the 1950s at Oak Ridge National Laboratory, where scientists used radioactive isotopes to track atoms moving through the body. The water in your body turns over in about 2 weeks. Half the water molecules in you right now were not there 16 days ago. You drink, you sweat, you urinate, you breathe out water vapor. The water flows through you like a river. The calcium and phosphorus in your bones, even your bones, the hardest tissues in your body, get replaced every year or so as the tiny crystals in your skeleton dissolve and reform. Your bones are constantly being demolished and rebuilt by specialized cells called osteoclasts and osteoblasts. Different tissues replace themselves at different rates. The cells lining your stomach last only about 5 days, constantly destroyed by stomach acid and constantly replaced. Your stomach lining is completely new every week. Taste buds last about 10 days. Red blood cells live about 4 months. Your liver regenerates every year or two. Some cells, though, are with you for life. Most of the neurons in your brain, the cells that hold your memories and make you who you are, were born when you were very young and will be with you until you die. Some neurons in your cerebral cortex are as old as you are. The cells of your eye lens, formed before you were born, will never be replaced. So here is a strange thought. The atoms that made up your body when you were 10 years old are almost entirely gone, scattered to the winds, literally. Some of them are in other people now. Some are in trees. Some are in the ocean. Some have been breathed in by a stranger on the other side of the world. The atoms that were you at age 10 are not the atoms that are you today, and yet you feel continuous. You remember being 10. You feel like the same person. So what is it that persists, if not the atoms themselves? It is the pattern, the organization, the information. Think of it like a whirlpool in a river. The water flowing through the whirlpool is constantly changing. New water comes in, old water flows out. But the whirlpool itself, the pattern, persists. The whirlpool is not a thing made of specific water molecules. It is a dynamic pattern that water molecules temporarily participate in. You are like that, a pattern that persists while the material flows through. Or think of a flame. The flame of a candle is not made of any particular molecules. The molecules are constantly changing. Fuel coming in, combustion products going out. But the flame persists as a pattern, a self-sustaining process, as long as conditions allow. You are in some sense a very complicated flame. Now, someone might say, if our atoms are constantly being replaced and we are still the same person, then what actually changes when we die? That is a good question. Let me try to answer it carefully. When you are alive, you are what physicists call an open system. You are constantly exchanging matter and energy with your environment. Food comes in, waste goes out, heat radiates away, new atoms replace old ones. But there is a pattern that maintains itself. Your cells keep working together in a coordinated way. Your heart keeps beating. Your brain keeps firing. The pattern sustains itself by consuming energy and maintaining organization against the natural tendency toward disorder. That tendency toward disorder is called entropy, and it is described by the second law of thermodynamics. The second law says that in any isolated system, entropy tends to increase. Things tend to become more disordered, more mixed up, more uniform. Heat flows from hot to cold, never the reverse. A drop of ink spreads through a glass of water. It never spontaneously concentrates. A glass falls off a table and shatters. The pieces never spontaneously reassemble and jump back up. Why? Because there are vastly more disordered arrangements than ordered ones. Think of a deck of cards. There is only one way to arrange it in perfect order, ace through king in each suit, but there are about 8 times 10 to the 67th ways to arrange it randomly. If you shuffle the deck, the odds of getting perfect order are essentially zero, not because physics forbids it, but because the disordered arrangements overwhelmingly outnumber the ordered one. Life fights against this tendency toward disorder. Every living thing is a temporary pocket of low entropy, a temporary island of order in a universe that trends toward disorder. But it takes work. It takes energy to maintain that order. You have to keep eating, keep breathing, keep burning fuel to stay organized. The physicist Erwin Schrödinger, in his famous book, What is Life?, pointed out that living things feed on negative entropy. They take in ordered energy-rich molecules like glucose and excrete disordered waste like carbon dioxide and water. The price of maintaining your low-entropy body is increasing the entropy of your surroundings even more. Life does not violate the second law. It just shifts entropy from inside to outside, while overall entropy still increases. When you die, that fight ends. The pattern stops sustaining itself. The coordination breaks down. Your cells stop working together, and the second law takes over. Without oxygen, your cells begin to die within minutes. The enzymes that were busy building things start breaking things down instead. Bacteria that live peacefully in your gut, held in check by your immune system, begin to multiply and spread. Within hours, they are consuming you from the inside. Decomposition releases carbon dioxide back into the atmosphere, nitrogen compounds into the soil, water. Over weeks and months, the complex organic molecules that made up your body are broken down into simpler and simpler compounds. The atoms that were organized into you disperse. Some of your atoms become part of the soil, some get taken up by plant roots, some are eaten by insects and bacteria, some evaporate as gases and drift away on the wind. Your carbon atoms might end up in a blade of grass. That grass might be eaten by a cow. That cow might be eaten by someone in a restaurant across the world. Your atoms, the ones that were briefly part of you, become briefly part of other living things. This is the carbon cycle. About 90% of all carbon dioxide returned to the atmosphere each year comes from decomposition, from the breakdown of dead organisms. Without decomposition, carbon would get locked up in dead bodies, and the whole cycle would grind to a halt. Decomposition is not just the end of life, it is what makes new life possible. Here's a remarkable thing to consider. The carbon atoms in your body have been around for billions of years. Some of them were probably once part of a dinosaur. 100 million years ago, a dinosaur breathed in, ate plants, incorporated carbon into its bones and muscles. Then it died, decomposed, and that carbon went back into the cycle. Plants pulled it from the air. Animals ate the plants. Microbes broke down the dead. And so on for 100 million years, atoms cycling through countless living things until some of that carbon ended up in the food you ate last week. And now it is part of you. And consider a glass of water. The molecules in that glass have been cycling through the hydrological cycle for billions of years. Some of those molecules evaporated from a prehistoric ocean, fell as rain on a Jurassic forest, were drunk by a dinosaur, excreted, evaporated again, fell again, flowed through rivers and underground aquifers for millions of years, and ended up in your glass. You are drinking the same water, made of the same oxygen and hydrogen atoms that dinosaurs drank. And it goes the other way, too. Some of the atoms in you right now will, millions of years from now, be part of creatures that do not exist yet. You are connected materially, atomically, to the deep past and the deep future. But here is something even more immediate. Every breath you take connects you to everyone who has ever lived. Let me show you a calculation that physics students sometimes do, called Caesar's last breath. When Julius Caesar was assassinated in 44 BC, he exhaled a final breath containing about 25 sextillion molecules, a 25 followed by 21 zeros. That seems like a lot, but the Earth's atmosphere contains about 10 to the 44th molecules, so Caesar's last breath was just a tiny fraction. But over the past 2,000 years, those molecules have mixed throughout the entire atmosphere, spread around the globe. Nitrogen, which makes up most of the air, is remarkably stable. A nitrogen molecule can persist for millions, maybe billions of years. So those molecules from Caesar's last breath are still out there, spread uniformly through the atmosphere. And when you do the math, the numbers almost exactly cancel out. On average, every breath you take contains about one molecule from Caesar's dying gasp. Not metaphorically, mathematically, statistically. And it is not just Caesar. Every breath contains molecules breathed by Cleopatra, by Genghis Khan, by Leonardo da Vinci, by your great-great-grandmother. The air we breathe connects us to everyone who has ever exhaled. Let me pause and make sure I have been clear because this is important. Here is what we have established. Everything is made of atoms. The universe started with only hydrogen, helium, and a trace of lithium, all made in the first 3 minutes after the Big Bang. Everything else, every carbon and oxygen and iron atom, was made later inside stars. Stars fuse light elements into heavy ones. Supernovas and neutron star collisions create the heaviest elements. These atoms get scattered into space, form new solar systems, and eventually become part of planets and people. While you are alive, your atoms are constantly being replaced, about 98% every year, but the pattern that is you persists. When you die, the pattern stops being maintained and your atoms scatter back into the world to become part of other things. Your energy does not disappear either. It just spreads out and becomes less organized, and every breath you take connects you materially to every person who has ever lived. Now let us tackle a common misconception. Some people hear this and say, well, if my atoms go on existing after I die, then in some sense I am immortal. But this is not quite right. The atoms that make up you have no memory of being you. A carbon atom that was in your brain does not carry around some essence of your thoughts. It is just a carbon atom. 6 protons, 6 neutrons, 6 electrons, behaving exactly like every other carbon-12 atom in the universe. What made it part of you was its position, its relationship to all the other atoms, the pattern it was participating in. Once that pattern dissolves, the atom is just an atom again. The immortality of your atoms is not the same as your immortality. Your atoms will persist, but you, the pattern, the organization, the information, the particular arrangement that thinks and feels and remembers, that is what ends at death. Is this sad? I do not know. I find it fascinating and in a way beautiful. Here is a thought experiment. Suppose I told you that in 5 years, every atom in your body will have been replaced. Would you feel like you are going to die in 5 years? Of course not. You feel like you are going to keep living, just with different atoms carrying on the pattern. The specific atoms do not matter. What matters is the continuity of the pattern. When the pattern stops being maintained, that is death. But the atoms themselves are indifferent to the whole thing. Now here is something truly remarkable. How long do atoms themselves last? The neutrons inside a nucleus, bound together with protons by the strong nuclear force, are stable, and protons appear to be extraordinarily stable. Scientists have been looking for proton decay for over 40 years. They have built enormous detectors, tens of thousands of tons of ultra-pure water in deep underground mines, isolated from cosmic rays, watching patiently for a single proton to disintegrate. They have never seen it happen, not once. The current experiments tell us that the average proton must live longer than 10 to the 34th years. That is a 1 followed by 34 zeros. For comparison, the universe is only about 10 to the 10th years old, 14 billion years. The lower limit on proton lifetime is 100 trillion times longer than the current age of the universe. What does this mean? The atoms that make up your body are, for all practical purposes, immortal. They have already existed for billions of years. They will continue to exist for billions more, maybe trillions, maybe forever. They were here before the earth formed. They will be here long after the sun burns out. And you, for one brief moment in cosmic time, got to borrow some of them. You got to organize them into something that could think about where they came from. Now let me tell you about the far future, because it is relevant to understanding what happens to energy and matter in the long run. The second law of thermodynamics says the universe is heading toward a state of maximum disorder. Physicists call it the heat death of the universe. It does not mean things get hot. Quite the opposite. It means things get cold and uniform and still. In about 5 billion years, the sun will exhaust the hydrogen in its core. Without fusion to hold it up against gravity, the core will contract and heat up, causing the outer layers to expand enormously. The sun will become a red giant, swelling to perhaps 200 times its current size, possibly engulfing the Earth. Even if Earth survives, it will be sterilized. The oceans will boil away. Everything alive will be gone. Eventually, the sun will shed its outer layers in a beautiful planetary nebula, and its core will collapse into a white dwarf, a dense ball of carbon and oxygen about the size of the Earth but with the mass of the sun, slowly cooling over billions of years into a cold, dark cinder. Here is the timeline for the universe as a whole. In about 100 billion years, the expansion of the universe will have carried all distant galaxies beyond our cosmic horizon. The sky will go dark except for the stars in our own local group. In about 1 trillion years, the last new stars will form. The gas clouds needed to make new stars will be exhausted. In 100 trillion years, the last red dwarf stars will finally exhaust their fuel and fade to black. The universe will be dark. Over time scales of 10 to the 37th years, if protons eventually decay, even the stellar remnants will slowly evaporate atom by atom, and the black holes evaporate too. Stephen Hawking showed that black holes slowly radiate energy and shrink. A black hole with the mass of the sun would take about 10 to the 67th years to evaporate. Eventually even they are gone. What is left? Just photons, neutrinos, and maybe some electrons and positrons spread incredibly thin across an incomprehensibly vast, cold, empty space. No temperature differences, no energy gradients, no possibility of doing work. Maximum entropy, heat death. Everything you love, everything humanity has ever built, every star and galaxy and planet will eventually be dispersed into a uniform, featureless void. Is this depressing? Maybe. But here is another way to think about it. Right now, the universe is young, only 14 billion years old. The era of stars, the era in which complex structures can exist and life can flourish, will last for roughly 10 to the 14th years, 100 trillion years. We are at the very beginning. If the history of the universe were a 1,000-page book and the era of stars were the whole book, we would be on the first word of the first sentence of the first page. Stars have been shining for 14 billion years, and they will keep shining for another 100 trillion. We have seen 0.01% of the age of stars, and the universe did not have to be this way. The laws of physics could have been different. There could have been no stable matter, no stars, no planets, no life. But instead, we got a universe that makes carbon in stellar furnaces, spreads it through space in spectacular explosions, and allows it to clump together into planets where chemistry can become biology and biology can become consciousness. We are unimaginably lucky to exist at all, and we are unimaginably lucky to exist now in this brief window of cosmic history when the universe is interesting. When I look at a leaf, I do not just see a leaf. I see carbon atoms that were pulled from the air, that came from decomposed plants and animals that were exhaled by creatures living and dead for millions of years, that ultimately trace back to ancient supernovas. Every leaf is a temporary assembly of atoms that have been on epic journeys through space and time. When I breathe, I am taking in atoms that have been through countless other lungs, human and animal, over millions of years. Right now, as you listen to this, you are breathing in atoms that were once part of dinosaurs, ancient forests, Roman emperors, medieval peasants, and every other breathing creature that has ever lived. We are all connected, not in some vague spiritual sense, but materially, atomically, demonstrably. And when I think about death, I do not see it as annihilation. Nothing is annihilated. Everything is transformed. The pattern that is me will dissolve, yes. The organization will disperse. The low entropy island that I represent will melt back into the high entropy ocean of the universe, but the atoms will go on to be part of new patterns. Some of them will end up in other people. Some will end up in trees or birds or fish. Some will be breathed in by children not yet born. Some will eventually find their way back into new stars where they will participate in fusion reactions and maybe be scattered again by new supernovas to become part of new planets and new life forms in the distant future. There is a kind of comfort in that, I think. Not the comfort of personal survival, because that is not what this is, but the comfort of being part of something vast and ongoing, of knowing that you are made of the same stuff as everything else, and that stuff will keep existing and keep rearranging itself into new wonders long after you are gone. The universe is not wasting material. Nothing is thrown away. Every atom that has ever been part of a living thing will be part of living things again. I once stood at the seashore and thought about this. The waves, mountains of molecules, each one stupidly minding its own business, trillions apart, yet forming white surf in unison, ages and ages before any eyes could see, year after year, thunderously pounding the shore as now. For whom? For what? On a dead planet with no life to entertain. And then life appeared. Deep in the sea, molecules began to copy themselves. They made others like themselves, and a new dance started, growing in size and complexity. Living things, masses of atoms, DNA, protein, dancing a pattern ever more intricate, out of the cradle onto the dry land. Here it is standing. Atoms with consciousness, matter with curiosity. That is what you are. You are matter that has organized itself to the point where it can wonder about itself. You are the universe asking questions about its own nature. You are atoms contemplating atoms. And when you die, the universe does not lose any atoms. It just loses one particular way of asking questions. But here is the remarkable thing. The questions you asked, the thoughts you thought, they had effects. They changed other patterns. They rippled outward. Every conversation you have ever had changed someone else's brain slightly. Every book you read, every idea you shared, every moment of kindness or cruelty left traces in the world. Information propagates. Ideas outlast the brains that conceive them. The patterns you created in other minds, the ways you influenced the world, those can persist far longer than any particular arrangement of carbon and oxygen. Perhaps the most durable part of you is not your atoms at all. It is the patterns you created in the minds of others. Now let me tell you something that modern physics hints at, though we do not fully understand it yet. The atoms in your body, they are not really separate things at all. At the deepest level, quantum field theory tells us that particles are excitations of underlying fields. Think of a field as something that has a value at every point in space, like temperature in a room or the height of waves on a pond. Quantum mechanics says these fields cannot sit still. They fluctuate, they vibrate, and when they vibrate in certain ways, we see what we call particles. The electron in your eye and the electron in a distant star are fundamentally the same kind of ripple in the same underlying electron field. There is one electron field that fills the entire universe, and what we call individual electrons are just places where that field is vibrating in a particular way. This is why every electron in the universe has exactly the same mass, exactly the same charge, exactly the same properties. They are not separate objects that happen to be identical. They are excitations of the same field, like two ripples on the same pond are not two different ponds. They are two disturbances in the same water. The same is true of quarks, photons, all the fundamental particles. They are all ripples in fields that permeate all of space and time. So the separateness we see, the boundary between you and me and the air and the ground, that is a kind of useful approximation created by the particular way matter is arranged. At the deepest level, it is all one thing. Even empty space is not really empty. The quantum fields are always there, always fluctuating. If you could somehow remove all particles from a box, you would not have nothing. You would have the vacuum, which in quantum field theory is a seething, bubbling sea of virtual particles constantly appearing and disappearing. Field fluctuations that briefly create particle-antiparticle pairs before they annihilate each other. This is not just theory. We can measure the effects of these vacuum fluctuations. The Casimir effect is a measurable force between two metal plates placed very close together. The vacuum fluctuations between the plates are restricted while outside they are not, and this imbalance creates a tiny but measurable force pushing the plates together. We have measured this force. The vacuum is real, and it is busy. The Lamb shift, discovered in 1947, showed that the energy levels of hydrogen atoms are slightly different from what we would expect without vacuum fluctuations. The electron in a hydrogen atom is constantly being jostled by virtual particles appearing and disappearing around it, shifting its energy levels by a tiny amount. This shift was one of the great triumphs of quantum electrodynamics, matching experiment to 11 decimal places. Even nothing is not nothing. I do not know exactly what to make of all that. I do not think anyone does yet, but it hints that the unity we feel when we realize we are made of star stuff might go even deeper than atoms. It might go all the way down to the fundamental fabric of reality. So when you ask what happens when you die, here is the answer physics gives us. Your atoms scatter and become part of other things. Your energy disperses and becomes less organized. The pattern that was you dissolves, but nothing is lost, nothing is destroyed. It is all still here. It is all still part of the same vast, ancient, ongoing cosmic process that has been running for 14 billion years and will continue for billions or trillions more. You were never really separate from it anyway. The fields you are made of extend to infinity. The atoms you are made of have journeyed through stars. The energy you embody has transformed countless times and will transform countless more. You are a temporary eddy in a river of matter and energy that has been flowing since the beginning of time. Consider the hydrogen atoms in the water you drank this morning. They have been around since the first 3 minutes after the Big Bang. They are among the oldest things in existence. And now, 14 billion years later, some of those primordial atoms are arranged in such a way that they can contemplate their own origin. They can wonder about the Big Bang that created them. They can calculate the conditions in which they formed. They can understand the fusion reactions that will eventually transform them into heavier elements. That is extraordinary. That is what you are. Ancient matter organized by evolution and chemistry into a pattern that can understand itself. And yes, the pattern that is me will end someday. But the atoms will go on, the energy will go on, the effects I had on the world will go on, and that is enough. It has to be enough, because it is what is true. Now I would love to hear from you, knowing that every breath you take probably contains at least one molecule from Caesar's dying gasp, from Cleopatra's whisper, from a dinosaur's roar 100 million years ago. Whose atoms do you think you are carrying? Whose breath are you sharing? Leave your answer in the comments below.